Okay, here we are, the mole day 3. Lots and lots of math today, so let's get to it. We're going to learn how to do percent composition today. Percent composition is when we calculate the percent of each element that's in a compound. So in sodium chloride, how much of sodium chloride is made up of sodium, how much is made up of chlorine. So, and that's based on mass. So percent by mass, the formula is the mass of the element that's in the compound divided by the mass of the whole compound times 100. A lot of times I'll say it's the part divided by the whole times 100. So it's the part of the compound, it's the part of sodium chloride, that's sodium, divided by the whole thing. So I would have to add up the entire mass of sodium chloride. So part divided by the whole times 100. The percentages will all sum to 100 or someplace really, really close, like 99.8 or 100.2. So it'll be really close. All right, so this first one, calculate the percent composition of each element in water. So water is H2O. All right, so what part of water is made up of hydrogen? What part is made up of oxygen? So the way we do this is we need to calculate the whole mass. Okay, there are two hydrogens. The mass of hydrogen is 1.008, and in water there's two hydrogens. The mass of oxygen is 15.999, and there's one of them. So 1.008 times 2, 2.016. And then that's 15.999. So to find the mass of the whole thing, I'm going to add those guys together. When I add them together, I get 18.015 grams. So that's the whole, and these are the parts. So to find the percent that's oxygen, or I'm sorry, percent that's hydrogen, I do the 2.016, do 2.016 divided by the whole mass, 18.015 times 100. So let's see what that is. 2.016 divided by 18.015, and then multiply that by 100. 11.19, which I'm going to round to 11.2%. Okay, so what percent is oxygen? The percent of oxygen is that 15.999 divided by the whole thing, 18.015 times 100. So 15.999 divided by 18.015 times 100 gives me 88.8%. And if you add those two guys together, guess what? It's going to equal 100%. Told you. All right, second one, calculate the percent composition of each element in ammonium chloride. So ammonium is a polyatomic ion. Its symbol is NH4. And chlorine is just Cl. Ammonium's oxidation number is +1, and chlorine's is -1. So when we crisscross those, we don't need any subscript. So the formula is just NH4Cl. So we need to find the mass of that whole thing first. So nitrogen, the mass is 14.007, and there's only one. Okay, there are 4 hydrogens though. Hydrogen's 1.008 times 4 is 4.032. And then chlorine, there's only one of them, 35.453 times 1. So when I add all those together, I get, let's see, 14.007 plus 4.032 plus 35.453 gives me 53.492. 53.492, which is the mass of the whole thing. So we do the part divided by the whole times 100. We'll start with nitrogen. The part is 14.007. The whole, 53.492 times 100. That's actually times 100. Let's see. 14.007 divided by 53.492 times 100. And 26.2%. So we'll go 26.2%. Okay, what else? Hydrogen. Hydrogen, the part is 4.032 divided by the whole, 53.492 times 100. Times 100. Ooh, small percentage is oxygen. So we'll go 7.5% is oxygen. Okay, last, chlorine. So I'll do chlorine down here, running out of space. Chlorine is 35.453 was the part, divided by the whole, 53.492 times 100 equals times 100, 66.3%. 66.3%. So let's check our math here. We have our percentages over here. 26.2 plus 7.5% plus 66.3% gives me 100 even. So good. Did a good job. Just an extra check on it. So for these next couple problems, we're going to calculate the percent composition of oxygen only in each of the following compounds. So let's write the formula here. Magnesium is Mg plus 2 oxidation number. Hydroxide is a polyatomic ion, OH, with a -1 oxidation number. So I'm going to crisscross those, and my formula is going to be MgOH2. Alright, so I need to calculate the whole thing. All I'm going to want to find the percentage of is oxygen, but in order to do that I have to have the mass of the whole thing. So find magnesium on your periodic table. The molar mass of magnesium, 24.305 times 1. And then oxygen, there's 2 oxygens because that 2 on the outside of the parentheses gets multiplied by the 1 and the 1 here. Okay, so oxygen is going to be 15.999 times 2. And then the hydrogens also times 2. 24.305. Do that math. 15.999 times 2, 31.998. And then 1.008 times 2, 2.016. And add all those guys together. And 58.319. 58.319. Okay, so we only want oxygen, so the percent of oxygen is 31.998. That's the part, divided by the whole thing, 58.319 times 100. So let's see, 54.9%. 54.9% of magnesium hydroxide is oxygen. Okay, so let's keep going. Sodium sulfate. So we need to find the percentage of oxygen in sodium sulfate. Sodium symbol is Na. It has a +1 oxidation number. Sulfate is a polyatomic ion. Its symbol SO4, and it has a -2 oxidation number. So I'm going to crisscross those, and the formula is going to be Na2SO4. I need to find the mass of the entire compound. So sodium is 22.990. You've got to use your periodic table. Times 2 though, because I got 2 of them. Sulfur, 32.006, but there's only 1 of them. And then oxygen, there's a lot of oxygen, 15.999 times 4. Okay, so let's do this math. 22.990 times 2, 45.98. This one, there we go, 32.006, and then 15.999 times 4 gives me 63.996. To add them all up, 45.98 plus 32.006 plus 63.996 equals. That's the mass of the whole thing. So all I need is oxygen. The percentage of oxygen is the part divided by the whole thing times 100. %. So we're going to go 40. You know what? Let's go 45.1%. 45.1% of sodium sulfate is oxygen. So that, children, is percent composition. That's the first part of the math we're doing today. Second part of the math we're doing today, something called empirical and molecular formulas. In molecular formulas is a formula that has the actual number of atoms of each element in the compound. It's the real, true formula. It's the actual compound. An empirical formula is a reduced formula. It's the one with the smallest whole number ratio. So when we had to reduce subscripts for ionic compounds, those are all empirical formulas. For ionic compounds, the empirical formula will also be the molecular formula. That's just for ionic compounds. But for covalent compounds, empirical formulas can be different from molecular formulas. Okay? And we're going to figure out how to find out both. For example, consider the compounds dinitrogen pentasulfide and ethane. So that was a typo, so I went ahead and corrected it. The molecular formula for dinitrogen pentasulfide is N2S5, in which its ratio of N's and S's, nitrogens and sulfurs, can't be reduced any further. I can't reduce the 2 and the 5. The molecular formula for ethane is C2H6. Okay, that's the molecular formula. So the empirical formula for ethane would be C1H3. You just reduce those. They can both be divided by 2. So for dinitrogen pentasulfide, molecular and empirical formulas are the same because they can't be reduced. For ethane, the molecular formula is the actual true correct formula, but it has an empirical formula of CH3. We're going to learn how to calculate both, but it takes a whole lot of steps. So we've got this neat little rhyme here that helps us to remember how to calculate an empirical formula. And you know what? You've got to memorize a lot of things, and this is just something that you really need to memorize. When you get your data may be given as either a mass, an actual mass of the element, or percent composition of the elements, and then you just have to change it into mass. We need mass, though. So the rhyme goes, percent to mass, mass to mole, divide by smallest, multiply till whole. Okay, doesn't make a lot of sense when I say it, but watch. It is pretty easy when you put it into practice. Determine the empirical formula for a compound that contains 48.64% carbon, 8.16% hydrogen, and 43.20% oxygen. So step number 1, percent to mass. The way we go percent to mass is we simply change the percent sign to a G for grams. So percent to mass for carbon would be 48.64 grams. Percent to mass for hydrogen, 8.16 grams. And oxygen, 43.2 grams. Percent to mass. I did it. I changed the percent sign to a G. Mass to moles. So in order to find the number of moles of something, you have to divide by molar mass. So I'm going to take each one of these and divide them by their individual molar mass. Carbon, 48.64 grams, divided by its molar mass, which you find on the periodic table, 12.011. 4.049. Okay, next, hydrogen. We're going to do the same thing for hydrogen. 8.16 grams divided by the molar mass of hydrogen, which is 1.008. It's 8.095. And finally, we're going to do oxygen. Oxygen, 43.2 divided by the molar mass of oxygen, 15.999. 2.700. Okay, what we've just calculated are moles. So that's the moles of carbon. This is moles of hydrogen. This is moles of oxygen. So let's review. We did percent to mass, mass to moles, divide by smallest. Okay, that's a literal statement. Divide by the smallest one. Which one of these is the smallest number? Right, that one. So I'm going to divide each one of these by the smallest mole amount. So we'll start with carbon, 4.049 divided by 2.700. And I get 1.499. Okay, I'm going to do the same thing with hydrogen. 8.095 divided by the smallest, which is 2.700. .998. Okay, last one. Oxygen, 2.700 divided by 2.700 gives me 1. Okay, so the last step is then make whole. All right, that's not a whole number. Technically speaking, that's not a whole number. This is awfully close to a whole number. This is one of the times where it's okay if it's close to a whole number to make it a whole number. That is definitely not close to a whole number. That's right smack dab in the middle of a whole number. That's between 1 and 2. That one is really close to 3. So we're going to make that 3. There's 1 there. And this one, we need to make it whole. What number would you need to multiply that to make it whole? Yeah, so I'm going to multiply that by 2. That's going to give me approximately 3. If I have to multiply that by 2 to get it to be a whole number, that means I have to multiply all of these by 2. So 6, that's 2. These are the subscripts for the formula. So this is C3H6O2. You just determined an empirical formula. Congratulations, good job. Okay, percent to mass, mass to mole, divide by the smallest, then make whole, or multiply till whole. We'll do another one. We're going to determine the empirical formula for a compound that has 40.05 grams of sulfur, 59.95 grams of oxygen. So step number 1 is percent to mass. Okay, it's already got a G by it, so it's in mass. So I don't have to do that. Mass to moles. So I need to divide each one of these by their molar mass. So 40.05 divided by the molar mass of sulfur on your periodic table, 32.066. Oxygen is, let's see, 59.95 divided by 32.066. So let's do both of these. .248. We'll just go 1.249. 1.249. Oxygen. Did I really put oxygen? Was that crazy? Oxygen's molar mass is 15.999. What a nut. I duplicated it. So 59.95 divided by 15.999. 3.747. Okay, so we went percent to mass. Well, it's already in mass. Mass to mole. So it's 1.249 moles, 3.747 moles. Next step, divide by smallest. Well, that's the smallest. So I'm going to divide both of these by 1.249. That's equal to 1. That's equal to, don't know. Divided by 1.249. Ooh, look at that. That's a 3. We're going, that's a 3. What's the empirical formula here? There's my subscript. There's my subscript. SO3. Why didn't we have to then make whole? Because they were both already whole numbers. Duh. Percent to mass, mass to mole, divide by smallest, and make whole. So they were already whole numbers. So for molecular formula, it's a formula which specifies the actual number of atoms of each element in the substance. You have to compare the molar mass of a compound's molecular formula with the mass of its empirical formula. Okay, so I'll show you. Once we have the molecular formula is going to be equal to the empirical formula times a certain number. Okay, I'll show you. It's not really that hard. So we'll have to give you this. Sorry. We'll have to give you the molecular mass. Okay, find the molecular formula of a compound with a molar mass of 78.12 grams per mole and an empirical formula of CH. So this is my molecular mass. We need to find the mass of the empirical formula first. Okay, the empirical formula is CH. So it's going to be 1 carbon and 1 hydrogen. So I'm going to add those things together and see what I get. .019. So the empirical formula mass is 13.019. Well, we have the molecular formula mass up here. So the way we calculate, what we do is we take the molecular mass, 78.12, and we divide it by the mass of the empirical formula, 13.019. 78.12 divided by 13.019. Look at that whole number. That's a 6. Okay, that's 6. In order to get the molecular formula, we take the empirical formula and we multiply their subscripts by the number that we found. The molecular formula, multiply empirical formula by the result in step 2 to get the molecular formula. So it's going to be C6H6. Let me try another one. Find the molecular formula for a compound with 43.64% phosphorus and 53.36% oxygen and a molar mass of 283.88 grams per mole. This is a molecular mass. We need an empirical mass. Okay? In order to find the empirical formula mass, we have to find the empirical formula first. Okay? This is a big, long problem. All right? But we can do this. We learned how to do empirical formula. Remember, it's percent to mass, mass to mole, divide by smallest, and make whole. First thing we're going to do, we're going to go percent to mass. So phosphorus, 43.64 grams. Oxygen, 56.36 grams. Okay, that's percent to mass. Okay, we're going to go mass to mole. Percent to mass, mass to mole. So in order to get the number of moles, I'm going to divide each by its molar mass. The molar mass of phosphorus is 30.974 on your periodic table. Oxygen's molar mass is 15.999 on your periodic table. So 43.64 divided by 30.974. 1.4089. 1.4089 moles. Because that's what we did. We took the mass divided by the molar mass and we got the number of moles. Okay, we do the same thing here. 56.36 divided by 15.999. 3.5227. 3.5227 moles. Okay, we did percent to mass, mass to moles. Divide by smallest. Okay, so I'm going to divide both of these by 1.4089 because that's the smallest mole amount. That number is 1. That number, I don't know, divided by 1.4089. 2.5. 2.5. 2.5. Okay, so we went percent to mass, mass to mole. Divide by smallest, then make whole. That's not a whole number. What number do I need to multiply that to make it by to make it a whole number? 2. So I'll need to do it to that one also. Okay, these are my subscripts. So phosphorus has a subscript of 2. Oxygen has a subscript of 5. That's my empirical formula. I need the empirical formula's mass, okay, because I'm going to take this molecular mass, 283.88, and I'm going to divide it by the mass of P2O5. So I need to find the mass of P2O5. So phosphorus times 2, 30.974 times 2. 61.948. 61.948. And then oxygen, it's 5 of them. Oxygen times 5. So 15.999 times 5. $79.995. Okay, in order to find the empirical formula mass, I add these two things together. $141.943. 141.943. That's the empirical formula mass. I just found it. P2O5. That's 2 phosphorus and 5 oxygens. So I'm going to divide this, the molar mass that was given in my problem, by the empirical formula mass. 283.88 divided by 141.943. Look at that whole number. That's going to be a 2. So what I do is I take my empirical formula, P2O5, and I'm going to multiply each subscript by 2. So my molecular formula is P4O10. Okay, so you'll probably want to do some more practice, which we have plenty of it for you in your homework. So make sure you watch the homework video next.